Mhm. Did anybody figure out a strategy for carrying out this problem yet? It can't be done directly, at least not with the skills we currently have. We need two steps to do this one. I'm positive that some of you guys have done this already, but something we did in our lesson on Thursday, finding sides. We can find sides in non-right triangles if the triangle we're working with can be broken up into two right angle triangles, right? That's a terrible straight line. So like if you break this triangle up into a left hand one and a right hand one, then you've got this 50-degree angle and the flagpole is 10 meters. And we at this point we should be able to find a side length using SOHCAHTOA. The 3M people have been doing it for 2 days. It was review. You did it last year. The 3U people, same thing. It was review from last year. And then the other guy, 10 meters and 35 degrees. I'll call the bottom length Y. So you guys did a problem like this, except it was finding the height of a building, I think, or a flagpole, or something that it always is. I'll let you guys keep going on that strategy, and then we can just combine those together once we're done. All right, I'm gonna play some catch up here, and I'm gonna do the minimum amount of work just to save some space. This is what I want to see from you guys. So hopefully at this point we should be proficient in picking a trig ratio to use. Here we have the opposite want the adjacent, so we're going to use tangent ratio. And then because what we're finding is on the bottom, when we do our cross multiplication, we're going to get x is equal to 10 times 1, which is just 10, divided by tan 50. And then your scientific calculators can handle that no problem. I gave away all my good calculators, so I'm going to use this one. 50 tan equals. So I got about 8.4 meters. I'll wait 30 seconds, let you guys try the second one, and then put them together. I think it's 8.4 seems reasonable. All right, here I come along for the run. This one is actually basically the same, just with 35 degrees instead of 50 degrees. Sets up the same way. So remember, if you're solving this as a proportion, tan 35 is just a number, right? So we stick it over 1. But when you do 1 times 10, you don't need to write 1 times 10. That's just equal to 10. And then you divide by the third thing, which is the tangent of 35. So in these upper level math courses, we don't need to write out tan 35 as a decimal. This is enough. IMO, that means in my opinion. 35 tan. 14.3. Do you guys get those two values as well? See some nods? All right. So let's wrap this up. They are whatever 8.4 plus 14.3 is, 22.7 meters apart. Looks good. So that's a classic double triangle problem. At this stage in the game, very reasonable for 3M and 3U people to do a problem like this. Break a triangle up into two, do two SOHCAHTOAs, add or subtract your answers to answer the problem. Anything you guys want to chat about? All right, you guys try this next one. Kind of similar. This time we're interested in finding an angle, and if you guys dial in on that left, I know my left and right, that right-hand triangle, we're trying to find angle Y. We only know one side. We don't have enough information, but If you guys broke it up into two triangles, that might help you guys out. I'm gonna let you get going. I might just draw my right-hand triangle, left-hand triangle here. Right angle, 10 meters, and X. I'm gonna pass around each class's next stuff while you guys give that a go. Don't let me forget to resume. All right, here I come. What are we using for this one? Sine ratio, right? I'll add a few more things on here. So opposite hypotenuse, we're using sine x over 10. And because what we're finding is on top, I'll show this extra work, but we've been mentioning these shortcuts. When you're solving for x, we'll do 10 times sine 48, but then divide by 1. So we don't really need to write the divided by 1. We can just write x is equal to 10 times sine 48. So if what you're finding is on top, it's just multiplication. 10 sine 48 times 48 sine, about 7.4. I'll go 7.43 just to keep some accuracy since my next triangle depends on it. If you use 7.4, you're all good. Aha. Now we have enough information. We've got this vertical side, 7.43, the hypotenuse 12. So now you guys have enough to find y. This is a great question because it mixes in Thursday and Friday stuff into a double triangle problem. What are we using? Sine again? Yeah. Hypotenuse. Most of you guys are probably at the stage where you don't need to label the sides, but keep doing it if you need to. What do we got? 7.43 over 12. So minimum amount of work finding an angle we talked about Friday. You can just do inverse sine of whatever 7.43 divided by 12 is. Your scientific calculators, if they were sentient and can think and had emotions, they would love doing all that all at once. They are capable of doing that for fulfilling their purpose. But if you feel better just doing 7.43 divided by 12 and then taking the inverse of that, totally fine. I got 38-ish degrees. More blank stares than normal. Let me try that again. 7.43 divided by 12. Inverse sine. 38.3 degrees. What are you guys getting? Oh, okay. I should have just said 38 then. Okay. We'll just say 38. Okay, we're all good. All right, another double triangle problem. So just to be clear, so far in this unit, we're all in the same spot. 3M people did SOHCAHTOA, 3U people did SOHCAHTOA. We reviewed that Thursday, Friday, and we've warmed up here with a couple double triangle problems. So this is the kind of level I expect everybody to be at, kind of being able to solve a problem like this after today. The 3M people get a chance to practice a bit more, demonstrate some knowledge. 3U people, this is a day where we got to cover a bit more content. So hang on to your butts. Let's dive in. 3M people, I will hopefully be able to kind of circulate a little bit. But yeah, work with the people beside you to get different answers. One of you probably made a mistake. What we're doing, the 3U people, we're going to see today that some special angles have trig ratios that are exact. What do I mean by that? For example, can you guys just humor me and put in the sine of, I don't know, the sine of 34, sine 34? Sine 34 is 0.5591, blah, blah, blah. You guys get that too? Some angles, like can you guys maybe put in the sine of 30? Sine 30 is exactly 0.5, right? Some angles, some special angles have exact trig ratios. And today, I'm going to show you guys which angles those are. And then after today, you guys will just know the trig ratios for these special angles. To start, we're going to actually think about the sine, cos, and tan of 0 degrees. Can I encourage you not to spoil it and don't punch these into your calculator just yet? And just we'll kind of develop. Because this is kind of an interesting thing, right? Like a triangle with a 0 degree angle isn't much of a triangle, right? It's kind of weird to think about. But we can take the sine, cos, and tan of 0 degrees. So consider the little the dynamic geometry software I have up here. I've got just some random triangle drawn here, but this little angle B is fixed at 90 degrees. It's always going to stay 90. And right now, this angle is 24.3. Can you guys just observe what happens to the opposite side as I make that angle super tiny? And what happens to the adjacent and hypotenuse? What's the relationship between those as I make the angle smaller and smaller? So you guys, hopefully you can see as I drag this point down, the angle is getting smaller and smaller. And again, think about what happens to the opposite side as this angle gets smaller and smaller, and what happens to the adjacent hypotenuse. So observe, observe. This is pretty tiny. We're at 1.2 degrees, 0.9 degrees. I can't get much smaller. But have a look. Look at the hypotenuse. Look at the adjacent. Look at what happens to the opposite side. Let me do that again. Drag it up here. I'll even make these guys bigger because it doesn't matter. So I'm going to make this angle smaller and smaller and smaller. Again, what's happening to the opposite side? And what is the relationship here between the adjacent and hypotenuse? So can somebody maybe fill in the blanks here? As the angle gets close to 0, what's happening to the opposite side? Peyton? It shrinks, and what does it approach? It gets close to 0 too. Exactly. And somebody else, as that angle gets close to 0, what does the relationship between the adjacent and the hypotenuse look like? So I'll visualize it again. As the angle gets close to 0, what's happening to the adjacent and hypotenuse? Maybe somebody different? Okay, Peyton, go ahead. Yeah, I mean, at 1.4 degrees, my program can't even tell the difference to a hundredth of a decimal place. They actually get pretty close, right? Does that make sense, everybody? Let's summarize those on our page and then talk about what the sine, cos, and tan of 0 might be. Where are we? Here we go. All right, so I'll use my text tool here. So as Peyton said, the opposite side gets smaller. And I'm going to say gets close to 0. And the adjacent and hypotenuse, as that angle gets smaller, we'll say this, the adjacent and hypotenuse get close to the same way. I'll just say get close to. Get really, really, really close. All right, just with those two observations, we're now ready to state, and this is some brand new tech for you guys, the sine of 0 degrees, the cosine of 0 degrees, and the tangent of 0 degrees. We're going to think about it today in terms of SOHCAHTOA. So I'm going to grab my drawing tool here. So in terms of SOHCAHTOA, the sine of 0 degrees, well, as the angle got really small, the opposite side, that's a 0 degrees, the opposite side got close to 0. Hello? And it doesn't matter how big the hypotenuse is. Guys, so it's 0 divided by anything. It's 0. We've kind of shown the sine of 0 is equal to 0. That's pretty neat. Sine of 0 degrees equal to 0. What about the cosine of 0 degrees? We don't need an intermediate step here. Guys, if the adjacent and hypotenuse are basically the same length when the angle gets close to 0, what's any number divided by itself? 5 over 5, 12 over 12, 20 over 20. It's equal to 1. The cosine of 0 degrees is equal to 1. And I might just add in brackets here because the adjacent and hypotenuse are equal. And then how about the tangent of 0 degrees? Well, the tangent of 0 degrees, as we talked about, the opposite gets close to 0. It doesn't matter how long the adjacent is. 0 divided by anything is equal to 0. So a nice little argument that sine of 0 is 0, tan of 0 is also 0, and the cosine of 0 is 1. Can you guys take a moment? Your calculator spit out those values as well? Just convince yourself. It should, right? And can you actually, just to observe how those decimal values approach 0, can you guys just try getting closer and closer to 0 with the calculation of sine 10, then sine 1, and then obviously sine 0 is 0. What you guys should see is a kind of a progression of those numbers getting closer and closer to 0. This is just trying to convince yourself. So sine of 10 is 0.1736. I mean, that's small, but it's not quite close to 0. Sine of 1, 0.0175, if we round it correctly. And then sine of 0 equals 0. So you guys can see, hopefully, that as those values get close to 0, you can see them getting smaller. Cosine of 10 and 1 and 0, we should see those numbers getting closer to 1. .9848. Wow, that's already really close to 1. Cosine of 1. Oh, this one works even better. 0.9998. If you guys, some of you guys are taking chemistry, right? To 3 sig figs, that's just equal to 1, right? Am I using sig figs correctly? And then cosine 0 is equal to 1. And then just for your note's sake, let's just witness the progression for tangent. Tan of 10, 0.1763. Tan of 1 should be even tinier. 175. And then the tan of 0, 0. All right, 3 people, are you guys kind of convinced this is true? We kind of did it 2 ways, with a numerical approximation, and then hopefully that dynamic geometry software demonstration convinced you as well. Anything you guys want to talk about? These 3 values, you guys are just expected to know. But like, if we're honest with each other, you guys always have a calculator. If you're ever unsure what the sine of 0 is, you just check on your calculator. It's 0. All right, we're going to do the same thing for 90 degrees. I'm going to, and apologies for the single-sided document there. We're going to do a similar visual demonstration here, and just try our best. It doesn't work as good as the one for 0, but we'll try our best here. I'm going to make a smaller triangle here. All right. Now I want you guys to observe what happens when I make a triangle that has a really, really, really large angle, and I'm going to try to make that angle as close to 90 as I can. Right now it's 81.9. So I'm going to drag this down, and I'm going to stretch this up. I'm making the adjacent super tiny. Stretch this out. what are we at now? We're at 87.6. Observe the relationship this time between the opposite and the hypotenuse, and then observe what's happening to the adjacent side as the angle gets larger and larger. I'm not sure I can make this any smaller just with the resolution of my screen. I can make it kind of small. They're almost at 88.9. I think this is the best I can do. But doesn't the same thing kind of happen? It's just kind of like the opposite corner. When the angle is close to 90, the adjacent side is really tiny, right? It's close to 0. And when the angle is 90, the hypotenuse and opposite get close together. Does that make sense, guys? It's kind of similar to what happened with 0. It just the adjacent and opposite change roles. Let's jot that down. All right, the adjacent side, as the angle gets close to 90, the adjacent side gets close to 0. And then we'll use similar language as the front. This time, the opposite and hypotenuse get really close together. So I'll just use the same language. Adjacent or opposite hypotenuse get close to the same length. Hypotenuse. All right, and then we'll just use similar logic to get our exact values for the sine of 90, the cosine of 90, and the tan of 90. This is really neat stuff. Last year, you guys couldn't do sine. Well, I mean, you could have put it in a calculator. They didn't really have the language to describe the sine, cos, and tan of 0, 90 degrees. This time, it's the sine of 90 degrees that equals to 1. Why? It's because the opposite and hypotenuse are the same length. Opposite and hypotenuse are the same length. I'll just say are equal. The cosine of 90, well, in this case, the adjacent side gets close to 0. It doesn't matter how long the hypotenuse is. 0 divided by anything is equal to 0. Cosine 90 is equal to 0. But it's not. This is an exact carbon, not an exact carbon copy of what happened before. What about the tangent of 90? The adjacent. This time, it's the adjacent on the bottom that's equal to 0. And guys, what happens when you divide by 0 on your calculators? Get a math error, right? We say the tan of 90 is undefined. The sine of 90 exists, it's 1. The cosine of 90 exists, it's 0. The tan of 90 doesn't though, it's undefined. Let's explore a bit why that is, okay? So first of all, I've got some different numbers here, and let's just verify that the sine, as we get a number closer and closer to 90, does get us closer and closer to 1. Sine 85. Oh yeah, we're super close already. 0.9962. It's very possible sine 89.5 is just 4 nines to that many decimal places. Let's check it out. Yeah, it's like 0.99996. It's so close to 1. So hopefully you're convinced. Yeah, sine of 90 is 1. You should see something similar happening with cosine. As that gets close to 90, they should be getting close to 0. 85 cos 872. 89.5 cosine. Oh yeah, super small. 0087. And then of course cos 90 is 0. Hopefully you're convinced. But can you guys just take a second and do the progression for tan 85 to tan 90 and see what you get. I'll do a quick tour of the 3 amps. I'm going to pause my recording. Don't let me forget to restart. Okay, now we're going again. So if you're watching at home, we just summarize our results for sine, cos, and tan. All right, so now normally if this was grade 9U, you guys would be like, okay, I square root 2, I'll get a decimal, life goes on. But I would like you guys to just leave x as root 2. And you guys should be comfortable doing this. We worked with radicals last unit. I'm going to redraw my special triangle to the right here with root 2 added in there. Can you guys do this as well? A right angle triangle with angles of 45 degrees and 45 degrees that have legs of 1 will have a hypotenuse of exactly root 2. This is called your special, this is one of your special triangles, one of two. It's a 45, 45, 90 triangle. Always 1, always 1, always root 2. Why root 2? We just did that. We found hypotenuse. Now, having those, we can now actually just state exactly the values of sine, cos, and tan. Cosine 45. Let's just pick the bottom right one. Would you guys agree the adjacent side is 1? The hypotenuse is root 2, making the cosine of 45 degrees exactly 1 divided by root 2. Exactly. This is the exact value of cosine 45. It's also the exact value of sine 45 because the opposite is also 1. 1 over root 2 is the exact value of sine 45. And then what's the exact value for tan 45? The opposite, Graham? It's 1 because the opposite side is 1 and the adjacent side is 1. You just get 1. I might add just in brackets here, where did that come from? It's because 1 over 1 is equal to 1. Now, I might just, down here, can you guys do 1 divided by root 2 on your calculators? What's 1 divided by root 2? 1 divided by the square root of 2. I got 0.7071 when I did 1 divided by root 2. Do you guys get about 0.7071? What do you get when you do sine 45? You get the same value? You should, right? Because it all fits together. All right, but now we have this nice exact value. Anything you guys want to chat about? This is the third set of values you need to know the exact values of. 45 degrees, sine, cosine, and tan. Now, these ones might be harder for you to get on your calculator. Tan 45, your calculator will spit out 1. But you guys need to know how to develop these special triangles, where these come from. So the exact values of sine, cos, and tan are 45. Anything you guys want to chat about? All right, we got one more set of, 2 more sets of numbers to do actually. And it comes from one special triangle. Along with me, would you guys draw an equilateral triangle? I'll make it nice and big. We have lots of space. With side lengths of 2. 2, 2, and 2. Now, what are the angles in an isosceles triangle? All 3 sides are equal, which means all 3 angles are equal, and they equal 60. I hear people whispering. I'm going to tuck a 60 right in here, but just right in there for my diagram. Can you guys do this along with me? Can you guys divide that equilateral triangle in half by putting a line down the middle? We're going to cut that right in half. And then note 2 things. Did you guys agree that would make a right angle? And what would this, in this left-hand right triangle here, 60, 90, what would this third angle be? It'd be 30, right? Yeah. If you would, we're going to draw a kind of another phase to this diagram. I just want to focus in just on that left-hand side. What we have here is a 30, 60, 90 triangle. Currently, the way we drew things, we said the hypotenuse was 2. But can anybody reason out what the bottom side would be equal to? Remember, Why 1, Jesse? Splitting it in half, right? Exactly. This bottom side is exactly 1. And if you guys have a right angle triangle with 2 sides, you guys can find the third. Can you guys do something similar to up above? And can you guys find the exact value of this third side in this special triangle, a 30, 60, 90 triangle? Remember, you're finding a leg, right, with Pythagorean theorem, so it won't be root 5. If you get root 5, you add it. I might just do this right here to manage my space. 2 squared plus 1 squared. Nope, I did it myself. 2 squared minus, because we're doing hypotenuse minus leg. 4 minus 1 is 3. The exact value of that side is the square root of 3. Do you guys get that as well? That's just using Pythagorean theorem. So I'm going to draw this one more time. This is your second special triangle. A 30, 60, 90 triangle always has sides in these proportions. If the hypotenuse is 2, the shortest side is 1, and the medium side is exactly the root of 3. Can we just digest that for a moment? Are you guys okay where the 2, 1, root 3 came from? Tried to show it in stages there. We can now state the exact values of sine, cosine, tan 30. Let's dial in on the 30. So cosine of 30, the adjacent side is root 3. The hypotenuse is 2. The exact value of cosine 30 is root 3 over 2. The exact value of sine 30, opposite over hypotenuse, is 1 over 2. And remember earlier when I had you guys do sine 30, it came out to exactly 0.5, just like we have here. Yes, Peyton? Well, we're trying to find, I mean, you could use SOHCAHTOA, but we use Pythagorean theorem. Like if you have 2 sides in a right angle triangle, find the third side. Yeah, because we're interested in finding the exact values here. It's kind of the purpose of our lesson. Okay? If you just needed to find that side, an approximate value, sure, you could use SOHCAHTOA. The tangent of 30, check this out, opposite side is 1, and the adjacent side is root 3. The tan of 30 is exactly 1 over root 3. There's another set of exact values we have for those trig ratios, 30 degrees. Very cool. All right, I'll wait 1 second. Can you guys try? So dialing in on 60 degrees here. 1 is the adjacent side. Root 3 is the opposite. 2 is hypotenuse. What are the exact values of cosine 60, sine 60, and tan 60? I'll wait a second while you guys try those. Time-wise, we're good. We got one quick example, and then you'll have about a half hour to do the little task I have for you. All right, cosine of 60, adjacent is 1. Hypotenuse is 2, 1 over 2. The sine of 60, the opposite is the root of 3, and the hypotenuse is 2. Root 3 over 2. And hopefully you guys just noticed how these two things just swapped, which should make sense, because when you talk about these different angles, the opposite becomes the adjacent, and the adjacent becomes the opposite. So it makes sense that these flip-flop. Look at tan 60. For 60, the opposite is root 3 and the adjacent is 1. So when you flip 1 over root 3, you actually get root 3 over 1, or just the root of 3. This completes the 2 special triangles that I expect you guys to know, and the sine, cosine, tan of our 5 special angles, 0, 30, 45, 60, and 90. As part of the task I have for you guys, I have you guys put these on a nice little summary sheet that you'll have for later. But let me show you one quick application. We're going to find an exact side length here. Now you might be saying, Mr. Smith, why do I need the exact length of this ladder up the wall? In real life, you don't. But I'm not prepping you guys for like the workplace here. I'm prepping you guys for all sorts of university math courses, including maybe some pure mathematics courses at a university. In lots of those applications, we do need to work with exact values. So here we go. This is just a SOHCAHTOA size problem. We're going to use exact values. We've got a ladder 12 feet long. And we have an angle. It makes, you know what, guys? I think I'd actually rather, can you guys just humor me? Let's make this with the floor. I think a 60-degree angle with the wall, I would not climb that ladder. I wouldn't feel comfortable doing that. But 60 degrees with the floor makes me feel safer. Yes, with the wall would be like it's basically already fallen over. And we're going to find the height of the wall. I'll just maybe label it with an H. So if this was you guys in grade 10, you would just be like, okay, I want the opposite. I have the hypotenuse. I would go about my business. I'm going to use the sine of 60 degrees is equal to the opposite over the hypotenuse, which is 12. Grade 10U would now just slam this into your calculator and get a decimal value. Even us last week, but what I'd like you guys to do, we're going to leave things exact. We have an exact value for the sine of 60 degrees. It is exactly root 3 over 2. And now we'll just solve for h using cross multiplication. We're going to have 12 times root 3 and then divided by 2. And that's the exact value. And then we should just simplify if we can. And this one's not too hard to simplify. 12 divided by 2 is exactly, I almost said exactly 3, exactly 6. The height of the ladder, 6 root 3 meters, exactly 6 root 3. All right, so one more time. The reason we use these, you might be thinking it seems useless to find these exact values, but you guys know you're taking the 3U University Prep course. This is prepping you for 4U Math and Calculus to take all levels of university math courses, okay? So this is a point in the course where we are doing something you might feel is a bit abstract, but it's necessary. This is just when you learn it in your math journey. Yes, Jess? Where'd the 3 come from? Which 3? This 3? Go on the previous page. What's the sine of 60? You will need to, if you don't have it memorized. Now let's be clear. And I'm the same way. Like, I've been teaching for over 15 years now, and sometimes I forget if the sine of 60 is root 3 over 2 or 1 over 2. But here's what you would do on a test if you blanked. You would do right angle triangle, 2, 2, 2. You would draw that. You would draw a line down the middle. That's 60, that's 30, and that's 1, right? And then you would use Pythagorean theorem, and that would give you the root 3, and then you just read them from the diagram. Sine of 60 is opposite root 3 over 2. Okay? And part of your task is you guys are actually going to redraw these special triangles and summarize those special angles so that when you're studying later, you have something to go back to. Is that our pumpkin? For 3 people, you got a short task summarizing what we did in our lesson. This is so you can have this in your notes. You can always convert it. I'll be right there, okay?